This is EN2041 Thermodynamics. Lecture 14. So in this lecture, and of course this is another flipped lecture, so you're going to watch this this session in your own time, and then in the actual session, the teaching session, we'll discuss and we'll look at some simple applications and examples, just as we've done previously with the other lectures that have been flipped in this particular module. So in this one, we're going to look at refrigeration and heat pump cycles. So it's a bit of a strange one, really, because what we're going to do is take the principles that we've already learnt with the Carnot cycle and with the Rankine cycle as well, and we're going to turn them backwards. So in some people's minds, it's a bit strange to go from three systems where we looked at power generation, essentially, or work generation, which would be heat energy being converted into work in some fashion. So that could be the diesel cycle, could be the Otto cycle, the Brayton cycle, or possibly the Rankine cycle. And we're going to go from that into a system which turns power or work into heat. So we run the problem backwards. But by doing this, what we're really doing for ourselves is demonstrating how well we understand the principles of work and heat conversion in heat engines, which is the essence of thermodynamics in a lot of ways. So it may seem a bit out of place that we talk about refrigeration after talking about systems which really, I guess, are harnessing the power of heat. But how you should look at a refrigeration system is really a heat pump. So what we're doing is we're pumping heat, we're moving heat from one reservoir to another. And that's what we need to understand in this lecture, how what a refrigerator does is that it pumps heat from one location to another, and that makes it a heat pump. So really a refrigerator is a type of heat pump. And the other thing we're going to look at later on in this session is the application of heat pumps, where we take heat from a low temperature reservoir and we pump it to a high temperature reservoir. And you'll probably have difficulty getting your head around that. So a heat pump would be used where we could be taking heat from something that's cold and moving it to somewhere that's warm. So in essence, we're pumping that heat. That's a funny thing to understand. So let's take a look at this in a bit of greater detail. So I guess these are some typical heat pumps that you might encounter. So we've got a fridge or a freezer. This is a chest freezer that you can see in the top left-hand image. And perhaps you might want to ask yourself, how does it work? What does it do? Well, it's a heat pump, isn't it? It takes the heat from inside the freezer and it pumps it away. So in essence, the inside of the freezer gets cold, and there must be something on the outside of the freezer that gets hot. As a result of that, we take heat from a low temperature reservoir and we pump it to a high temperature reservoir, the high temperature reservoir being the outside, the ambient environment, which is warmer. And that almost, in some ways, it almost seems to violate the zero law of thermodynamics, which says heat always flows from the cold to the hot. But we'll show you how that's done later, because it's a bit of a trick, really. It's a thermodynamic trick. So in the top right-hand corner, we've got a typical industrial scale refrigeration unit. And this could be a very large-scale system supplying cooling to perhaps a building, or it could be an industrial chiller, that kind of thing. In the bottom right, what we have is the cooling section from an air conditioning unit, where the refrigeration cycle is used to cool down air or to pump heat from one location to another. And then in the bottom left hand shot, what we have there is actually a heat pump, where we are warming the house by extracting heat from the ground underneath. So in the large image, it's what's called a ground source heat pump. And in a ground source heat pump, we extract heat from the land underneath the house, and we pump that heat into the house, even though the heat that's in the ground is at a lower temperature than what's in the house. In many ways, it's just like a freezer, and you could compare it to the freezer example. So the thing being cooled is the land underneath the house, and the high temperature reservoir that the heat energy is being dumped into is the inside of the house. And then there's other examples in there of water being used as the primary heat source, as well as different kinds of configurations, horizontal loops or slinkies, as they're also known. Okay, so that's typically what industrial systems might look like. After the next slide, I'm also going to show you a video of somebody just talking quite generally about how a fridge works, which you'll also find useful. So the key things that we're going to get through in this lecture is 3 main points. First of all is understanding how a reverse cycle works. So I'm going to show you temperature entropy diagrams for a fluid, and that fluid isn't steam, but to all intents and purposes it may as well be steam. It is a fluid that undergoes a phase change whilst exchanging heat and work with its surroundings, and we need to find the appropriate data in order to calculate the energy that's being exchanged, just like we would do in a power station application for a forward cycle. So we're going to look at how reverse cycles work and how we can get cooling from work input, or really heat transfer from work input. We're going to look at the reverse Carnot cycle, and we'll see how we could take our understanding of the Carnot cycle and literally just run it backwards. So to turn work into heat, not heat into work. And we'll see how that relates to refrigeration processes. As usual, this will be highly idealized. So in subsequent lectures, we will then look at more realistic, more real systems. And then in the third case, we'll look at this idea of a concept called coefficient of performance. Now, coefficient of performance is very important to us because this is an equivalent factor for efficiency. But the problem with COP is when you calculate it, in many cases, it can be greater than 1. It can be perhaps 4 or 5. So it's almost telling you, if it was, let's say the COP was 4, if the COP was 4, that's telling us that it's 400% efficient, which as engineers in training or people with common sense even, we know that you can't have something that's 400% efficient. You can't make energy. So perhaps it's how our control volume, our boundary to our system is drawn that makes it look like it's 400% efficient. So a COP of a coefficient of performance of 4 means that I'm moving 4 times more heat than I am putting work in, but I didn't make that heat. I extracted it from a reservoir. So quite often we get confused between coefficient of performance and efficiency, and it's our job as the engineers to make sure that we're injecting the common sense into the argument. All right, so we'll do all this in the lecture. This is what you should be able to understand and demonstrate by the end of the lecture. What I want to do now is show you about a 4-minute video, which is very useful because it's a person who works with refrigeration systems, just showing us from quite a fundamental and quite a simple perspective how a fridge works. So watch the video carefully and make sure that you understand how a fridge works and what all the different components are. And then what I'll do is I'll build on that and we'll discuss the thermodynamics of it. But I want you to be able to see some of the components and what the throttle valve looks like and what the pump looks like and the practicalities of it. Because these are fairly straightforward systems that you and I can understand. They're not as complicated as an overhead camshaft or something like that in a reciprocating engine, which would involve huge amount of detail. It's a nice simple system that we can quite easily identify the components for and see where the thermodynamics is coming into play. So take a look at the video and then we'll expand on this with some of our theory.
Hi, I'm Matt from eSpares. In this video, I'm going to show you how a fridge works. And we all know it's important to keep fresh food in the fridge. The bacteria that can cause food to go off can't really thrive below about 5 degrees C, so keeping our food in the fridge keeps it fresh for longer. Now, the process of refrigeration is actually quite a straightforward one. If you lick the back of your hand and then blow on it, it starts to feel cool straight away. And that's because as that liquid evaporates off into a gas, it draws heat away from the skin. And in a fridge, we've just got a continuous process where a refrigerant is being allowed to turn from a liquid into a gas and then being turned back into a liquid again. Let's take a look at the back of this old Zanussi fridge freezer, and we'll start down here with the compressor. It's essentially an electric pump which is pushing a refrigerant around a closed system, first along the outside of the fridge, then the inside of the fridge, before finally returning back to the other side of the compressor to continue the cycle. Now in the old days they used to use ammonia as the refrigerant, and that was quite toxic. They then changed to Freon, which you may remember is the stuff that did the damage to the ozone layer. This fridge freezer uses isobutane. It doesn't really matter what the refrigerant is, it just needs to be a substance that can easily turn from a liquid to a gas and back to a liquid again. So starting on the high pressure side of the compressor, our refrigerant gas gets very hot, much like a bike pump gets hot as you put the air under pressure when you're inflating a tyre. And that heat is radiated away in this condenser coil. It's like an ordinary household central heating radiator. And you can actually feel when it's on that it's very hot on this side, getting cooler as you move across, so that by the time it's over here, our refrigerant has cooled down sufficiently to be condensed into a liquid where it goes and sits in a reservoir at the bottom of the appliance. Our liquid refrigerant then passes into this thing, which is called a filter dryer, and that just traps any contaminants, removes any moisture, which is important because the refrigerant now passes into this, what looks like a wire. It's actually a very fine capillary pipe, and that feeds up to the inside of the fridge to the evaporator coils. Now on your fridge or freezer, you may not be able to see the evaporation coils. They're probably behind a panel at the back or in the top of the unit. But on this hot point fridge freezer, you can actually see the evaporation coils here. They form part of the shelf structure. So after passing through that fine capillary, our refrigerant liquid passes into this much larger diameter coil where it's allowed to expand and evaporate into a gas. And that draws the heat away from inside of the unit. Now at this point, the pump or compressor is now drawing that gas through the whole system to be recycled and used again. Everything's encased in a very thick layer of insulation to make sure that the only heat that's drawn away is from the contents and the inside of the freezer. Most fridges would be cooled by evaporation coils in exactly the same way, although on some fridge freezers cold air is simply drawn up from the freezer unit into the fridge. Now the big problem with the whole refrigeration process is that every time we open the door we let moist air in, and that moist air condenses into water which needs to go somewhere. On a fridge it condenses onto this back panel where it drains down and out through this drain hole. And in the freezer compartment that moisture builds up as frost. In a freezer like this you'll need to manually defrost by turning it off and draining away the water as it melts. On a frost-free or auto-defrost freezer, the compressor will periodically stop, and there are heating elements around the evaporator coils which will heat up, melt away the frost, and that water will drain away at the back of the appliance. And all that water ends up in this evaporation tray. And that just sits on top of the compressor, so it's nice and warm, and that just evaporates all that water away. So there we go, that's how a fridge works. Now if you need any spare parts for a fridge or freezer, you can find them for all makes and models on the eSpares website. Thanks for watching.
Well, thanks to Matt there from eSpares, and you know, if you ever find yourself needing parts for fridges and freezers, don't ever hesitate to give him a shout. All right, well, hopefully that was a valuable introduction to what it is refrigerators do, and you should have got the opportunity to see the various components. Now that you have a decent understanding of those things, let's go through the thermodynamics of an idealized process, and then obviously in the subsequent lectures we'll convert idealized into real world. So first of all, we have to remind ourselves that this is the reverse of power generation. So we take work and we turn it into heat, or we move heat using work, not the other way around, as I've said previously. So we put power into a cycle to pump heat from one location to another. And in the example you've just seen in the refrigerator, we pump heat from the inside of the fridge or the freezer to the outside. And it's not really relevant which is the high and low temperature reservoir. What we're doing is we're pumping heat to the outside, which means that it must get cold inside, and that's what we want to do. So the first thing that we would commonly use a heat pump for is to refrigerate or cool a process. So that could be in food refrigeration, it could be in air conditioning, or it could be in process cooling on industrial scales. The other thing that we might want to do, and this is the bit that gives us some confusion, is we might be doing what's called upgrading of heat. So we take heat from a low temperature reservoir and we move it to a high temperature reservoir, all right? So in the case of a fridge, that's exactly what we do. We take the heat from the low temperature reservoir inside the fridge and we pump it out to a high temperature reservoir, and we can do that because of the reverse cycles that you're going to see in a minute. Now you can actually use that for heating your house. So heat pumps in heating applications do that. They take heat from underneath a house or from a body of water nearby, or even sometimes from the air, and they pump the heat from the low temperature to the high temperature reservoir, and hence you get heating within your house. So it's nothing revolutionary or new in that respect. But the use of heat pumps in domestic heating is slowly coming more and more into fashion. But there's a lot of financial considerations to take into account, which we're not going to do in this module, but you'll probably learn later. So previously we've looked at power cycles, so where we receive heat at the high temperature reservoir and we reject it at the low temperature reservoir. So just think of all the stuff that we've already covered on steam. That's exactly right, isn't it? We take it from the high temperature, we reject it down to the low temperature, and in doing so, work is done by the fluid on a turbine, for example. But we're going to turn that the other way around, aren't we? And I know I'm labouring the point, but you really need to understand that, otherwise there's going to be a lot of confusion. All right, let's move on and start looking at this from the perspective of our thermodynamic analysis. So we're doing reverse cycles, aren't we? So we take heat from a low temperature reservoir and we reject it at a high temperature reservoir, and work is being done on the fluid, not the other way around, not the fluid doing work on some of our mechanical drives. Our mechanical drives are doing work on the fluid, which is what you saw with that video where the pump is doing work on the refrigerant in that case. So the term heat pump is normally applied to a machine that takes heat at an elevated temperature, whereas a refrigerator is used to extract the heat. But it's really the perspective at which you're looking at it from. They're both doing the same thing. It's just a question of perspective. So if I have a heat pump that's taking heat from underneath my house and is pumping the heat into my house, it's just like a refrigerator, but the thing that's being refrigerated is the ground underneath my house. That wasn't my intention, is to take the heat and move it. And in a fridge, we're taking the heat and we're moving it. That's exactly what we're doing. So it's just a question of perspective, I guess, really. So heat pumps are starting to become more widespread in terms of practical application of heat provision. And one of the reasons is the need to produce heat from electricity, but from a relatively low energy source of electricity. So imagine the practicality of me putting a solar panel on my roof and then using that small quantity of energy to try to drive something like an element heater, so like an electric fire or an oven. You know that's going to be quite impractical. I'm going to have to store all that energy up and then discharge it suddenly and get really impractical performance, whereas a heat pump is something where you can take a small quantity of heat and just keep it ticking over, just keep slowly upgrading. And also I'm getting more than I put in, aren't I? So if I'm taking heat from one reservoir and pumping it into another, the amount of electrical energy I need will be smaller than the amount of heat that I can usually realistically pump. And that's coefficient of performance, which we're going to learn about later. So for renewable applications, heat pumps are starting to become more in vogue. But the problem with heat pumps is they're very poorly understood by non-engineers. And I guess the reason is because they don't do this module. So, I guess salespeople and politicians and perhaps activists that want to get this technology out there they're not really looking at their control volumes properly. So this is why we do this, so that we can understand our control volumes properly. Okay. So here we have it. This is the TS diagram for the Carnot cycle, operating in the way in which we're used to seeing it. But obviously what I'm going to do is just turn it backwards. So it shouldn't look any different. So obviously this is going to be somewhat impractical for refrigeration processes. Yeah, we understand that. We understood that this is somewhat impractical for power generation, but it allows us to theoretically define the problem first off. So looking at the TS diagram we've got here, this is just the Carnot cycle, and you should already understand this. So have a look at what's happening between 1 and 2. We call that the boiler, don't we? We're driving at a high temperature reservoir. We are drying out our fluid, come down to between 3 and 4, and we are condensing our fluid at the low temperature reservoir. So the only difference from our textbook thermodynamics approach between the forward Carnot cycle, which we've already seen, and the reverse Carnot cycle is we're just going to turn this problem backwards on itself. Okay, so let's actually do that. All right, so if my animation worked, then what you should see now is that the Carnot cycle is running in reverse. I've simply just inverted the arrows, haven't I? So they run the other way. But rather than taking that for granted, let's make sure we understand what that is. So now the cycle is actually going to run, how shall we run it? Let's run it 2, 1, 4, 3. It doesn't really matter. It's going in reverse. So we could go 1, 4, 3, 2. It doesn't really matter. Let's think about what's going on then. So the boiling, if you like, part of the process, the drying out of the fluid or the evaporation part of the process is now between 4 and 3. Notice it's at the low temperature reservoir, and that's right, that's how your fridge works. And then look at the condensation process. The condensation process is acting between 2 and 1. That's at the high temperature reservoir. So it's not just a question of saying, oh yeah, it's the Carnot cycle in reverse. It's understanding that the processes themselves have been reversed, or the temperature reservoirs have been inverted as well. So where we had compression, we now have expansion. Where we had expansion, we now have compression. From a textbook perspective, that's easy. We're just running the process backwards. But the purpose of this lecture is to see the fundamental thermodynamics, and then couple that with the practical things that we're seeing from looking at the design of a fridge, or having somebody walk through how refrigerants work with us. All right, so in a bit more detail then, what we've got here is the TS diagram that we have reversed. So the condensation between 2 and 1, the compression between 3 and 2, whereas that was normally expansion. Working in the same way, just in opposite locations. Isothermal evaporation between 4 and 3, and then isentropic expansion between 1 and 4. Nice and straightforward, as I previously said. So heat is moved from the low temperature reservoir to the high temperature reservoir. So instead of saying boiler now, what we say is evaporator. And I'm going to show you the location of the evaporator, etc., in the next couple of slides. So we don't say that a fridge has a boiler in it. We say it has an evaporator in it, or it has a series of evaporation coils within it. And if we were to calculate the Carnot efficiency, everything would start to go a bit wrong. Think about the Carnot efficiency, where we talk about the amount of let me get this right, because we now got to go back to our steam theory. So the Carnot efficiency is the amount of work provided versus the amount of heat energy we put in. But if we were to now calculate the Carnot efficiency for a reverse cycle, we'd have an efficiency greater than 1. By logic, the value is going to be greater than 1 in most cases. So we don't talk about something called efficiency anymore, because you'd have more than 100% efficiency, and then that would really kind of confuse you. So we use this term called coefficient of performance. And what coefficient of performance is telling us is how much thermal energy is being moved per unit of work energy that's being put in. So the reason we get something more than 100% is not because we've magicked or conjured up energy from nowhere. We know that fundamentally we can't do that. What we're saying is that the reservoir held a certain amount of heat, and you can almost think of heat as like a fluid being pumped, really. We're pumping heat, but the heat was already there. So the amount of work required for the pump to pump a fluid containing a certain amount of heat isn't really a function of the amount of heat that was in the reservoir. So if we do it right, we can pump a hell of a lot of heat only using a small amount of work. And when you do the theoretical calculations based on the refrigerants and the enthalpies, just like we'd normally do for a power station, what we'll get is a value much greater than 1. So we get very confused customers and we get confused people that work with us because they don't understand it the same way we do. They think that we've made energy out of nothing. And they say, wow, it's amazing, you've got a 400% efficiency. So just to keep us all sane in many ways, we use this term coefficient of performance. It means the amount of energy that's been moved per unit amount of work that's been put in to move that heat energy. So this is our refrigeration system drawn as a process diagram and as a TS diagram. Now you're happy with the TS diagram because you've seen it on a couple of previous slides. So really the key to this slide is to just identify the components as we've seen from the previous video where Matt was going through all the different parts of the refrigerator. So let's look at the process diagram without seeing the different components so that we're not allowing our eyes to guide us on seeing components we've seen before. So let's start at point number 1. So we go through the condenser, going from 1 to 2. Okay, so sorry, I'm going wrong. Let's start at point 2, going to 1. You see, I'm not getting used to my nomenclature. So from point 2 to point 1, we have the condenser, right? That's the high temperature reservoir, the condenser. So the fluid is being turned from a gas more or less into a liquid, which is what we wanted to do, and in doing so it is rejecting heat. Okay, so think of the part of the fridge where the heat rejection is taking place. Then it goes through the expander, so we're going from 1 to 4. Okay, so that's the expander. We started off with a fluid. It's being expanded, so therefore it boils, it turns into a gas. Okay, and the expander is then dumping work out. So what you're going to find out in subsequent lectures is that we don't have moving expanders in fridges. We just replace them with a very simple component. But we're going to play this fundamentally. So we're going to imagine that there was an expander, there was a turbine in there. Okay, then from the expander into the evaporator. So we take heat in. So think of the part of the fridge where heat is taken in at the low temperature reservoir. We get a phase change, no change in temperature. It's just like the forward Carnot cycle. So we have heat going in, which gives us evaporation. Then out of the evaporator, so we're at point 3 now, and then into the compressor where we do work on the fluid. Okay, so that's from 3 to 2. So we go right round. Let's put some pictures into our diagram so we can see now how that identifies with a modern refrigeration process. So the compressor is the pump, isn't it? That's the function of the pump. It's the compressor. It compresses the fluid. In doing so, it raises its temperature, as we can see, and it upgrades the fluid to the high temperature reservoir. Okay. So the evaporator compartment is the bit inside the fridge, isn't it? It's taking in heat because evaporation needs heat in order to take place. It takes in the heat from the food, I guess. So heat is slowly leaking into the fridge all the time because no insulation is perfect. So heat is slowly leaking in from the outside world, and then that heat is being pumped back out again. Or you can think about it as if you were to put a container full of water in there in order to freeze the water or cool the water down. You're going to need to pump heat out of the inside. Well, what is the expander? It's actually just a throttle valve. So we don't have moving parts. There's no point. We're not trying to harvest work from what we're doing. Things will get very messy. So all we need as an expander is literally just a small hole. And as the gas flows through the hole, it expands just like a typical expansion process. And the condenser, well, the condenser is the back of the fridge, isn't it? It's that black radiator where we are rejecting heat at constant temperature. And have a look at the TS diagram to convince yourself that you understand what's going on. So it's the condensation process in our reverse Carnot cycle. So the heat is being dumped out of the back of the fridge or freezer into the ambient environment, and you can prove that to yourself when your fridge is running. Just put your hand on the back, feel this grill if it's on there. It depends on the design of the fridge, and you notice it's warm because it's throwing heat out. Okay, so in many ways this is the most important slide of the whole lecture. You need to understand how the TS diagram relates to what's happening in a real refrigeration process. If you can get this, you're set up quite nicely to understand the rest of it. All right, so what we're going to do now is just to get you to have a slightly better understanding of the process. Is I'm going to show you a short video where somebody's actually playing around with refrigerants. So it's quite good fun. And what this demonstrator is doing is she's showing us how the refrigerants are turning from liquid into gas or gas into liquid, and it will help you to understand what's happening internally in these processes that we're seeing in front of us. Now, in many respects, that substance you could be seeing there may as well be water, and it's changing phase over a much broader temperature range, and you know, the boiling and condensation process temperatures you'd be used to. But she's using a refrigerant in this case, so what we're actually doing is we're seeing how the refrigerant behaves. It's very useful to see this video. Try to then look at this from a different perspective. So this is the behavior of the refrigerant versus the practical behavior of a fridge itself, which we saw in the previous video. So have a look at it, maybe ponder about what it all means, and then we'll get back to the thermodynamics.
This model shows how a refrigerant changes state, transferring heat in the form of latent heat as it does so. The refrigerant in this closed container has partially vaporized, and the vapor fills the tubing and the second container. The small amount of pressure in here acts on the refrigerant and prevents it boiling, even though the surrounding or ambient temperature would normally allow that to happen at atmospheric pressure. If we remove latent heat from the vapor with this iced water, the refrigerant condenses, and the pressure drops because the vapor in here takes up less space. The reduced pressure allows the refrigerant to boil at a lower temperature, and we can see bubbles as vapor is released. If we remove the ice water, condensing stops, the vapor pressure builds up, and then the boiling of the refrigerant stops. The fine point at which vaporization or condensing starts and stops, depending on which way the change of state is occurring, is called the saturation point. Because the liquid is saturated with heat just before the change to vapor. And when condensing, the vapor is saturated with heat just before it changes to a liquid. It only takes a slight change in either the pressure or heat content of the refrigerant to change the saturation temperature. If I heat the refrigerant with this hot water, the extra heat makes it boil, and the pressure in the tubing will rise. The increased pressure raises the boiling temperature, and when that's the same as the water, a new saturation point is reached. Changes in pressure or temperature directly affect the saturation point. If we were to imagine a situation where we wanted to transfer heat from a hot space to a cold space, then a simple closed system like this would do the trick. Refrigerant absorbs latent heat and boils in the heat exchange unit called an evaporator. The vapor travels to the other coil, the condenser, and gives up latent heat as it condenses. The liquid then returns to the first coil and the cycle continues.
Hopefully that was helpful, because it gave you an idea of what it is a refrigerant is doing when it's changing state and when heat is being transferred across the boundary into and out of the refrigerant. I think it's worth saying that if you did just come out of that video sequence feeling more confused, not less confused, then don't worry, just put it out of your mind for now, and we'll just carry on in looking at the textbook definition. It should have been helpful for you to see the refrigerant boiling and condensing, and seeing how in a process that wasn't being controlled by a throttle valve, in that case, you can just see how there's that equilibrium between the liquid and the gaseous phase, which is very typical of a liquid exerting vapor pressure on its surroundings. But don't worry if it was confusing to you. It should have just given you perhaps a nice practical introduction in how the refrigerant is behaving in the different parts of the process. All right, so let's get back to coefficient of performance then. So this is our sort of hybridized expression for efficiency, but we're not going to use efficiency for describing heat pumps and refrigerators, because it would be a complete misnomer. So in the industry, they say coefficient of performance, and quite often you'll just hear people talking about COP. You sometimes hear CP, but not really. It's mostly COP. So when refrigeration designers get together and they discuss who's got the best design, it will pretty much be driven on COP. There'll be a cooling effect as well, the temperatures they can reach, but it's COP that they obsess over. So this is an expression that you will feel familiar with, because it looks very similar to how you might calculate efficiency. So this is the ratio of the change in heat at the output side versus the supplied work. Okay, so if we were looking at a Carnot efficiency for a power station, it would be work versus heat. And I always say to you, divide by the thing that costs you money. So in the case of a power station, the fuel is going to cost me money, so I divide by that. But in the case of a refrigeration process, let's assume that it's electricity that we're buying in order to get our refrigeration effect. So that's the input to the process. So we would express COP as Q in. So that's the heat that's flowing into my heat pump or my refrigerator versus the amount of work that I had to put in overall. We're going to leave it as net work, but there's only really one device that's consuming work, and that's the compressor, that's the pump, isn't it? So the COP is going to be Q divided by W, and in many ways you would think of that as efficiency, but we're going to call it coefficient of performance. So Q in is the heat supplied in this case for a refrigeration system to the hot side reservoir. Okay, to the hot reservoir, and W is the work consumed by the pump. Now, as we go through these slides to the end of the lecture, I'm going to get you to write one or two things down and then compare them. So if you don't have a pen and a paper handy, just pause the video, go off and get a pen and a paper, and write these things down as I say, okay, write that one down. So the first thing I want you to write down is this: for a refrigeration process. So write refrigeration and then write COP equals Q in over W net. Okay. So once you've got that, we're going to move on, because what we'll do is we'll actually compare that to our heat pump later on. Okay. So now what we're going to do is just quite a simple thermodynamic analysis, and it should be no different to any Carnot theory that you may have done previously, or even the Carnot stuff that we've done so far in this module. So we'll look at it in terms of the first law of thermodynamics, which is just energy flowing around the place. So COP would be the heat energy in the evaporator, because that's the bit we're interested in this case. So it's the heat energy in the evaporator versus the heat energy difference between the evaporator and the condenser. Okay, but it's the evaporator I'm interested in. So just as we would use any normal forward Carnot theory, I can turn those Q's just into temperatures. So I want you to write this down again here, which is in the case of a refrigerator, COP equals temperature in the evaporator versus the difference in temperature between the condenser and the evaporator. So write that one down as well. So COP equals T evap divided by T cond minus T evap. And it's going to throw up that little kind of innocuous looking expression there is going to throw up an interesting problem later on. And it's an interesting performance problem that every single refrigeration system suffers with. So the temperature in the evaporator is equal to T4, and that's also T3, isn't it? So that's the low temperature reservoir, and the condenser is T2 and T1, so that's the high temperature reservoir. If you're confused at all, that's fine. Just jump back and have a look at the TS diagram. That's all we're doing. Okay, so if we've got that, let's move it on a little bit. So in a refrigeration system, the COP is expressed as this. And what we're going to do is we're going to look at a heat pump later, but we have to realize that with a heat pump, our point of reference is actually slightly different. So let's look at our refrigeration system. The COP equals minus Q43 divided by the difference in work in the process. So W32 plus W14. Remember, one's going to be negative anyway. Okay, so write this one down. Refrigeration, COP is minus Q43 over W net, if you like, or W32 plus W14. But interestingly, it's Q43 that is my cause for concern. That's the perspective at which I'm looking at the problem. So in my fridge, the part that I'm pumping heat out of is where I'm interested in, isn't it? So that's the part inside the fridge itself. So it's the so if it's 4.3, then that's going to be the evaporator condition. Okay, it's the evaporator I'm interested in. All right, now it's nice and straightforward and simple, but we're going to look at it in a slightly different perspective in a minute. So now we come to look at a heat pump. A heat pump is the same thing as a refrigerator, but I've got a different area of interest for my heat pump. It's the same system, same cycle. In many cases, we use the same refrigerant. The temperatures might be slightly different. Not always. Sometimes they're the same, but it does the same thing, but we're interested in a different part of it. So TS diagram in the bottom right-hand corner, nothing to say. We already know it. It's the same thing. The components have the same names, the energy flows are in the same directions, and the nomenclature is exactly the same. Nothing different there at all. Let's now have a look at the system diagram for it. Okay, I'm going to use the same nomenclature. I'm going to use the same numbering convention as well. So I have a condenser, expander, evaporator, and compressor. But let's see what they look like in terms of a heat pump. Well, my compressor does the same thing. My compressor is just a pump, and it's moving refrigerant around the process. Okay, we're happy with that one. Now, my evaporator, if you remember from last time with the refrigeration process, the evaporator was where the food is stored, and it pumps heat out of the thing to be refrigerated. In a heat pump, that's not what I'm interested in. I don't build a heat pump because I'm trying to cool down the land or cool down some water or something like that. That's not the idea. The evaporator is the source of heat, which I'm going to move. It's a low temperature reservoir, and I'm going to pump it out of the process. So in the case of a heat pump, my evaporator is usually a great big body of land which is underneath the house or possibly in the garden. So have a look at this in your own time. So some installers, they'll dig your garden up and they'll put the evaporator coils in your garden and put your topsoil back on. Or in other cases, we use if it's a what's called a water source heat pump. So what we're looking at now is a ground source heat pump. But in a water source heat pump, it could be a lake. There are such things as air source heat pumps as well, where they extract heat out of the air. So my evaporator is the ground, and that's what I'm pumping the heat out of. But that's not why I'm building it. That's not what is of interest to me. So Q43 isn't that much of an interest to me. It's a different part of the process. So W14 is an expander, okay, and in a realistic sense, it's just going to be a throttle valve, just as before, okay. But for thermodynamics, we're going to say, or imagine there was work in the expander. It doesn't really matter. It will come out as 0 in a practical example. It's just going to be a throttle valve, the expander. But now comes the interesting bit. So the condenser is I guess it's the central heating system in the house. So there will be radiators in the house, or there will be more coils in the house, or some form of energy release, thermal energy release going inside the thing that I want to heat. So the condenser is the high temperature reservoir. The heat is being pumped from the low temperature reservoir, the evaporator, into the high temperature reservoir, the condenser. So this diagram, just possibly, compare it to the fridge. So in the case of the fridge, the food compartment is the evaporator, and that black radiator where we're just dumping heat to try and get rid of it is the condenser. But in the case of the heat pump, the condenser is the central heating system within the property that's being warmed itself. So actually, in this case, the focus of my attention, where I'm going to set my thermodynamic solution up, is from the perspective of the condenser, not the evaporator. It was the evaporator for the fridge or the freezer, but for the heat pump system to provide heat, it's the condenser that is the focus of the calculations. That's where the heat is going. That's what I'm interested in. The work process is still the same, but the heat is going out to the condenser, and that's what I want to do my calculations based on. All right, so let's go and do that. So finding the coefficient of performance is going to be nominally the same, but it's going to be Q21 I'm interested in, not Q43 that I'm interested in. So the first line is the same, but then in a heat pump system, the COP is Q21 over the net amount of work. So that's Q32 plus Q14. In the case of practical cycles, there is no work done in the expander. It's just a throttle valve. Okay, so therefore I've set up a different equation. So what I want you to do is I want you to write down that one. So I want you to write heat pump and then write COP equals Q21 divided by W32 plus W14. Look at that, and now look at the one that you wrote down previously for the refrigeration system and look at the differences between them. Very simple. And then when you see that, you'll understand the next line, which says, therefore, the coefficient of performance for a heat pump is actually equal to the coefficient of performance for a refrigerator plus 1. All right, so that's why they're different in that respect. Why are they different? Because it's where my interest of where the heat is going. In the case of the refrigerator, the heat is actually it's the heat in the expander I'm interested in, not in the not in the other part of the process. Okay, so it was because in a heat pump it's Q21 and in a refrigerator it's Q34. Okay. So we should already understand that it's theoretically possible for the coefficient of performance to be greater than 1. So in a heat pump system, the COP is always greater than 1, and so we never say efficiency. It confuses us. If we actually look at how a heat pump is set up, a heat pump is the purest form of a reversed power cycle. So the Carnot, the nominal normal Carnot cycle is the reciprocal efficiency, isn't it? So it is what we're interested in is the amount of work we get per unit transfer of heat, but in a heat pump is we're interested in the amount of heat transfer we get for a unit input of work. So that's why we've got COP as 1 divided by efficiency of the forward power cycle. That should be fairly logical based on everything we've said up to this point anyway. So we do actually come up with some very interesting limitations. So go back to the things you wrote down, and you'll notice that, again, we're working on things such as delta T. So when I ask you to write that equation down where it showed what the coefficient of performance was based on temperatures, and whether it's for the fridge or for the heat pump, it doesn't matter. It's the same thing in this case. As the temperature difference gets larger, so look at your equation that showed the temperature form of the COP. As the temperature difference gets larger, the COP gets lower. Now that's obviously the opposite to what we learnt in power cycles. To maximize our efficiency, we maximize the temperature difference. But this is a reverse cycle. So to maximize our efficiency, we minimize the temperature difference. which is a stupid idea. And I guess this is where the really interesting part of this is. So to maximize the COP, we have to minimize the temperature difference. So I would now go to my client if I'm designing this and say, you wanted the best COP? Okay, here's the fridge. I've set it up for the best COP, and the temperature inside is 1 degree cooler than the temperature outside. And let's imagine it's a warm day and it's 25 degrees. The temperature inside my fridge is now 24 degrees. So your customer is going to say, this is not fit for purpose. I don't want it. So the bigger the driven temperature difference with a heat pump or with a fridge, the worse off the COP gets. So what does that mean? First of all, let's look at our fridge. So that means the bigger the temperature difference you run on the fridge, i.e. the colder you make your fridge or your freezer, the less efficient it is. It still works, but you need much more electricity to drive it. So that's not such a good idea. So that's why, for other obvious reasons, like it's just going to be working harder to keep the temperature down. That's why we have to consider carefully what temperature setting we actually need, because that's a real pain. That's the laws of thermodynamics working against us, isn't it? But then, so for a fridge, for example, the temperature difference will be that much. A freezer obviously is going to be a lot more, but if the temperature in your fridge is maybe about, 4 or 5 degrees Celsius, you could be looking at you could be looking at maybe a 10 or a 20 Kelvin temperature difference. It's not too bad. We can live with it. We get a reasonably good efficiency. Efficiency, not the right word, but we get a reasonably good performance, a typical setup conditions, and we're happy with that. And that's that's the nature of a fridge. We've got to buy the electricity anyway, so around about 10 degrees, we're happy with that. Now the problem starts to come in with heat pumps. Is that the heat pump is going to be driven from the other side, isn't it? We're going to have a set point temperature that we want. So if the outside environment is very, very cold and I'm upgrading heat from one source to another internally, so I'm upgrading very cold heat energy to much warmer heat energy, my coefficient of performance will be hopeless. It will be really bad. I could be trying to drive over a 40 or 50 Kelvin delta T. So yeah, let's take an example maybe of really cold outside, perhaps sub-zero down in the ground or the water, the air that I'm pumping from, and I want. It's not necessarily the temperature of the ambient environment. Maybe I could be trying to maintain 20. It's not that. It's the temperature of the refrigerant inside the radiators. Now, radiators themselves, I mean, what temperature are they going to run at? They're going to be around about 40 degrees Celsius, perhaps. I've got a huge delta T in that case. And what it means is that the COPs, they really start to plummet, and you start to get really poor COP. And in a lot of cases, and this is why heat pumps can be a little bit controversial, in a lot of cases, the COP creeps below 1, which is telling you that the amount of work energy that you're putting into it, you're getting slightly less heat energy back. So from the perspective of paying my electricity bills, I may as well have just used the electricity in the normal way of just passing it through a coil to heat up to heat up a heating coil, just as I would have done with an electrically fired heater. So it gets very tricky. It gets difficult on how we make these decisions. And for that reason, heat pumps sometimes can be a little controversial. You have to run them for longer because they won't give you, really raging hot radiators like you might be used to if you had a gas-fired system. So I'm not saying they're a bad thing. I'm saying there's a lot of things we have to tackle. We'll also get reversibilities if we're pumping very hard against big pressures. So you get things like flow and separation losses as the refrigerant screams across the throttle valve, etc. So these are all really interesting things that we need to consider if we're going to model these systems and how they work. But the driving factors all come from what you've seen in these examples here. So what we've covered in this lecture, you should now understand heat pumps and refrigeration cycles and how they work. You should understand the concept of the reverse Carnot cycle and what it means. You definitely need to understand this idea of coefficient of performance, how it differs from nominal forward Carnot cycle efficiency, and what the significance is, and this idea of as delta T gets larger, the COP gets lower, and in cases where the delta T is significantly high plus all our other losses, we may actually see less than 1 COP, and then the process itself starts to get drawn into question. So what we're going to look at now is more practical ideas, and obviously we're going to take our Carnot cycle, our reverse Carnot cycle, and we're going to look at what we need to do in order to make it much more practical, in the same way that the Rankine cycle is more practical than the Carnot cycle. So have a think, two-phase flow, that kind of thing. Do we really want to deal with 2 phases in our refrigerator pump, or are we going to do some subcooling and superheating just as we would do in a power station forward Carnot cycle?